Hello, my name is Carneiro, and I'm a graduate research assistant at the University of Colorado Boulder. I would like to acknowledge my co-author and advisor, Hans-Peter Schaub. So the topic of this presentation is on a novel architecture for numerical multi-satellite simulations. And I would like to also acknowledge that part of this research was supported under the NASA STTR Phase 1 grant. So let's start with the motivation. So let's say you have a piece of software, right, that is normally used for single satellite simulations. How do you take that and use it for multi-satellite simulations? Well, you might start off with a block of code that's called code block 1. And this is where all the lines of code that generate the spacecraft, that run the simulation, that set up the environment is in, right? And so if you want to run a multi-satellite simulation, you might start off by adding a loop to it, right? So instead of having just one spacecraft that is being simulated, you just loop through however many you want to simulate, and that's that, right? And that might work, but what if one of the spacecraft is different than the other? Well, you might say that you just add another code block, right? Code block number 2. And, again, that might work, but you can see how this quickly becomes complex and rather cumbersome, right? So especially if you want to simulate, hundreds of satellites, this is not the way to go, right? So how do we simulate multiple satellites in an efficient way? There are obviously multi-sat simulations bring new challenges, and the goal of this work is to answer some of these questions. How do we optimize the code in terms of modularity, in terms of, and also ease of coding, right? How do we make it easily scalable for hundreds or thousands of satellites, right? And how do we parallelize the processes such that we minimize that linear increase in simulation time when we add another spacecraft, right? So the solution is to create an architecture that is built from the ground up with multi-satellite simulations in mind. And for this work, we relied on 4 underlying principles. The first one is modularity. We want the architecture to be broken up into smaller pieces such that the developer can readily change those pieces and run a new simulation, right? Scalability, we want the architecture to be able to simulate hundreds or thousands of satellites. Parallelization, to increase the speed of the simulation, and scriptability, which is how easy it is for the developer to create new code, to read older code, that sort of thing. So I'm going to present you now the architecture framework, and this is it. So the architecture framework is composed of different classes. The master class is the only one that is not part of the simulation. It doesn't have any modules that are run at simulation time. What it does do is it has the methods and the functions that create, manage, and access all other classes. So first of all, we have this environment class. There's only one per simulation, and it is shared among all spacecraft. And it's in this environment class that all the gravitational bodies, the ground modules, the atmosphere, SRP, all of that is simulated. All those modules related to the environment are simulated here. And then for each spacecraft, we have a dynamics class and a flight software class. The dynamics class defines the properties of the spacecraft. That is, its mass, its inertia, tensor, what sort of attitude control devices it's carrying, how big the thrusters are, the size of the battery, what's the shape of the solar panels and where they're pointed at, that sort of thing. So everything related to the spacecraft properties is defined and is simulated in these dynamic classes. And then the flight software classes is where the flight modes and attitude control laws are implemented. And that's the code that would be uploaded to a flight computer. And to add more spacecraft, one simply needs to add another dynamics and another flight software class, and it's as easy as that. And the user can have all the dynamics and all the flight software classes be the same for all spacecraft. You can have the same dynamics class for all spacecraft, but then each one has their own flight software class. You can mix and match. It's really up to the user to define these and to create the classes as it suits them. So now I want to talk a little bit about the process and the module design. And first of all, I'd like to talk about the software that we used. I purposely only talked about this now and not before, because the architecture that we're proposing really is agnostic to any particular software, right? The structure that we're proposing and then the whole architecture is just is on its own. It's not tied to any piece of software, right? But now it makes sense to talk about the specific software that we used. And the software that we used is called Basilisk, which is our in-house software. It is a software framework that is capable of both faster than real-time, but also real-time with hardware-in-the-loop simulations. And it's being developed by the AVS lab and LASP, which is the Laboratory for Atmospheric and Space Physics. It was first developed to support the Emirates Mars mission, but now it has sprawled and is used in a lot of different companies. This piece of software really is tied to astrodynamics research, whether that is modeling orbits or modeling the attitude of spacecraft systems. So in Basilisk, each module is assigned to a task, right? And then each task is assigned to a process. And for this work, each of the classes that I mentioned, the environment and then the dynamics and flight software classes for each spacecraft, each of them contains its own process. However, whereas the environment and dynamic processes only contain one task where all the respective modules are contained inside, each flight software process contains multiple tasks. And that is because we want each task to correspond to a different flight mode. And in Basilisk, we can enable and disable tasks, right? And so if we want to change a flight mode, we simply enable the one we want to be active and disable everything else. And that makes it so certain modules are active at certain times and then others really aren't. Another important thing to consider is the initialization and execution orders. These are really important for the simulation to run as expected and for the modules to have access to the information at the right time and to have the most up-to-date data to run the math and to run the simulation, right? For this work, the initialization and the execution orders are identical. And the first modules to be initialized and executed are the ones related to the environment. And that's because the environment is self-contained. It doesn't depend on any spacecraft. And so, we just propagate the orbits of the gravitational bodies. We update where the ground locations are depending on the rotation of the planets, that sort of thing. Afterwards, we update all the dynamics classes. And that's where, the spacecraft orbits are propagated. That's where the attitude is recomputed, that sort of thing. And then the simulation takes the data from the dynamics class and feeds it to the flight software algorithms, right? And they have the most up-to-date information about where the spacecraft is and where it's pointing and what's the status of the battery, that sort of thing. And that information is then used to change flight modes if necessary, or compute the requested torque through the control law, right? And then once those decisions are made and once that information is processed in the flight software classes, then that influences the next time step and the next dynamics class, right? So I wanted to finish off with some simulation examples, and the first scenario is quite simple. It's just Earth as the main planet, and three spacecraft in orbit around it. And if we look at the code snippet right here, we see that we first import the planet environment, right? In this case, it's called environment Earth, and then we import the dynamics and the flight software classes, which in this case are all homogeneous. And obviously, since we want to simulate three spacecraft, in this case, the variable number of spacecraft is equal to 3, right? Well, what if we want to, for example, change the type of environment, right? If instead we want to be orbiting around Mercury, right? Well, that is quite easy to do. We simply change the first line of that code snippet, and instead of importing the environment Earth, we now import environment Mercury. Now, obviously, the user would have had to define this this class beforehand, right? But once it's defined, the user can just readily swap between the two, or between how many they need to, just by changing one line of code. And you know, that's a really powerful tool for analysis and for, you know, changing small things in your code or in your environment and having substantially different simulations, right? Then the final scenario is going back to Earth, but with more satellites. Instead of 3, we use 6, right? And if you look at the code snippet here, it doesn't change. It's exactly the same code snippet as the first example, right? The only thing that's different is that the number of spacecraft variable is now equal to 6, right? And because we define the initial conditions in a loop, and it loops through all the spacecraft, you know, we don't even need to change this code snippet. And again, it's exactly the same as the first one, just that the number of spacecraft is now equal to 6 instead of 3, right? I also wanted to show some multi-threading results. These are quite preliminary results, but you know, we can really see that when we parallelize the processes and when we take advantage of the architecture of modern CPUs, that we can really decrease the simulation time and make these simulations more efficient, right? And because the architecture is built from the ground up with multi-satellite simulations in mind, the spacecraft don't have to be run in series, and so we can save a lot of time there.